Okay? Conservation of mass. By the way, you can do the same things with conservation of momentum. It's a lot more work. I will not torture you with that one. But you can just work it all out. It's all there. And you get the following equations. Let me write them down. Conservation of mass in the x direction gives you the following. See, just even writing it all down takes a ton of time. All right, v dx, h u v. Okay, here it is in their full glory, conservation of mass, momentum. So very simple concepts from physics applied to a mass, and you say, I have, even a constant density mass, and these are the equations of motion of this thing. And this gives you equations that determine how the fluid moves around and how the amplitude of this fluid gets modulated. Now, we're going to make some assumptions, because this is still too hard. First assumption is going to be that H is constant. Well, it's not really constant, is it? But what we're going to assume is, for instance, if I'm over the Gulf of Mexico, the height of the troposphere there is, maybe it's 7 kilometers here, 7.1 there, 769 there. Who cares? It's 7, roughly, approximately, to leading order. Okay? So we're going to just assume that this height of this too shallow fluid is constant somehow. And that's going to make our lives so much better. Because when you do that, look at what happens to the first set of equations. dH dt. Well, if h is constant, that thing is 0. And then you just simply get the following. du dx plus dv dy is equal to 0. This is called the incompressibility condition. Okay? So this is called incompressible flow. Basically here, you can't squeeze the liquid. Like, if you squeeze here, it comes out here. So with gases, you can compress them, right? So this is why you can go to Home Depot and buy yourself an air compressor. We're going to assume you can't do that. Okay? You're going to say incompressible. So this is certainly in fluids. You can't take water and say, I'm going to take this water and by squeezing super hard on it, I'm going to make it fit in my water bottle. Okay? That typically is not going to work for you. But you could take gas and put a bunch of volume gas in a small area. So incompressibility means that you can't squeeze this thing, essentially. That's what it sort of means. But it gives us a condition here. This is kind of a famous condition. Have you guys heard this condition before? So anybody's taking fluid, this is like one of the major things. You say, you know what I'm going to do? I'm going to work with incompressible flow. Why do you work with incompressible flow, by the way? Because you are in trouble if you do not work with incompressible flow. I showed you there, and if you want to solve that full thing, hey, go to town. Yeah,
well, that's the other reason is it's reality.
Yeah, it's mostly reality. But they use this also times in atmospheric flows. It's a nice condition because you can still make progress in your life. Okay? All right. The other two equations reduce down reasonably well to the following. du dt plus 2u du dx plus d dy uv is equal to f v dv dy plus d dx uv. Now notice, these are still a little bit more complicated. They're nonlinear. Notice how u and v couple here, how you have u du dx here. So this is like a quadratic type term here, here, and so forth. And so it's still a fairly complicated system, even in this case. But you can do algebra, a lot of it, and you can make some simplifications happen. And in particular, yeah.
Gravitational constant? Or
Yeah, that's right. Use gravity. F is the Coriolis force. So, yeah. Okay. All right. So now, let me just highlight to you what you would do so we can get down to our result. What you would do with this is you would take the y derivative of this and the x derivative of this, spend a bunch of time and waste a bunch of paper. Do it once, do it twice until you like get all your bugs out of the errors, and then like all these amazing cancellations and magic just happens, and then you kind of know it's right. Like when all this stuff just cancels and adds together beautifully, then you know like I did all the algebra right. Okay, unless you get 0 equals 0, then maybe you did it wrong. But it comes out very nicely, and let me just show you the final form of this. If you do all that, and then you remember the definition of vorticity, which is erased, here's what you get. There's the vorticity dynamics. And remember that the vorticity itself is defined as omega is equal to dv dx minus du dy. Right? So actually simplifies significantly. So this is the equation we're going to be interested in with this definition of vorticity. So this is why vorticity plays a big role in fluid dynamics, because in some sense, when you think about solving the fluid problem, yes, you want to find the velocity of the fluid in the u and v direction, but sort of in some sense, as you do this reduction, you learn very quickly that in some sense the right variable to work with is not the velocities in each individual component, but rather this quantity here, the vorticity, which somehow combines information about the velocity in each direction into a very nice representation. Okay? All right. Now, there's one other thing that people have done to think about this model, and which is they have decided to introduce a thing called a stream function. And it's actually kind of a handy little deal. Okay? So you're learning all kinds of fluid dynamics today, and again, purely for enjoyment. Hopefully you're enjoying it. Yeah? Okay. Here is the stream function idea. I'm going to define this quantity called a stream function, which is going to be the following. The stream function is going to reproduce for me the velocity field. Okay? That's how we're going to define this. Now, why would I do this? That's a good question to ask, right? It's like, why would you introduce extra variable? Let's just take a look at what it buys us for a moment. So first of all, what it's really suggesting I do is not represent. Notice that with vorticity, we decided to represent the dynamics with this other quantity. The vorticity somehow captures both the x and the y fluid motion. But it's a really convenient way to represent it. And in some sense, that's what the stream function is going to do for us. So first of all, let's ask about the stream function in the context of incompressible flow. Now, the incompressible flow condition is this. Ux plus Vy is equal to 0. So I'm going to start replacing partials with just subscripts to be partials. So what is u of x? Well, take the x derivative of it. Let's put it now in stream function form. The u of x derivative is minus phi that, right? So I just take the x derivative of both sides. I get that. Plus Vy, take the y derivative of this. And by the way, we know that partial differentiation can be interchanged. So I have phi xy minus phi xy. So this is 0. So in other words, the incompressibility condition is automatically satisfied by the stream function. Nice. So now we can say, great, if I go to the stream function, and once I can calculate it, I already know it satisfies one of my major constraints about incompressible flow. How does this stream function relate to vorticity? It's another question to ask. All right. Let's calculate it. Omega is equal to dv dx. Well, v is psi of x, so that's going to give us psi xx minus du dy. Okay, so I take the u there, which is psi y, which is negative psi y. So the negative and a negative makes it a positive. I get this, which is Laplacian, and there you are. Okay, so the Laplacian of the stream function is equal to the vorticity. And then the vorticity dynamics given by this equation. Okay? Let's put it all together. And what I'm going to do is write everything in terms of stream function and vorticity, which somehow represent the natural variables of the system to be working with. Now, when you do that, you end up with the following. And I'm going to add one thing in here, which I didn't carry through in the derivation, but you can bring it in either empirically or through a derivation by including dissipative effects, and I'll tell you that in a minute. Here it is. Here are the equations where this bracket is the following. Psi of x, omega y, minus psi of y, omega x. These are a set of equations we're going to solve. And what this is a diffusion term. So the vorticity itself diffuses, loses energy. Okay? So for instance, these hurricanes that are formed, they start to form what makes them go away. Well, eventually you just dissipate that energy either through heat, through frictional forces in the atmosphere. There's stuff that just stops this thing from moving around. We just put that in there as a diffusion term, which basically acts as some way to dissipate away the energy. So what does this tell you? Well, okay, it tells me the evolution. How does the vorticity move in time? And here's the equation for that. But it also tells me that in addition to that, I have to have the stream function. And the stream function is determined by whatever my vorticity is at any point by Laplace's equations. Okay? Now what's awesome about this, and you may not think this is awesome, but I like this, and you're going to like it too. And here's why you're going to like it. You're going to make awesome movies of big vortices moving through your computational domain, and you'll be like, dang, I'm awesome. That's what you should be saying like in a couple weeks, 3-4 weeks time when you have cool vortices moving across your computer screen. And if you can't get excited about cool vortices, then I don't know. That's exciting to me. Cool pictures. All right. I'm hoping you're excited about that. I'm not feeling it right now from anybody, but you're going to feel it then. You'll be doing cool stuff with this.